What if the very fabric of reality was woven together by a single, mysterious event at the dawn of the universe? Picture this. The moment the cosmos was born, something extraordinary happened, something so strange and powerful that it still echoes across the vastness of space and time. This is the story of the universe's first quantum entanglement, a phenomenon that defies our everyday understanding of how things work. Quantum entanglement is like a cosmic thread connecting particles across unimaginable distances, instantly linking them in ways that baffle even the sharpest minds. But here's the real mystery. How did it all begin? Was it a fluke, a cosmic accident, or was there something more profound at play? In this video, we're diving deep into 30 mind-bending theories that attempt to unravel this enigma. Each one offers a unique glimpse into the origins of the universe and the strange, tangled web of quantum physics. So, if you're ready to explore the secrets of the cosmos and uncover the universe's first entanglement, keep watching. You're about to embark on a journey that will challenge everything you thought you knew about reality. Now let's turn our attention to the very beginning of everything, the Big Bang. This colossal event, often described as the birth of the universe, might also hold the key to the first quantum entanglement. Picture the universe as a single, infinitely dense point called a singularity. In those initial moments, as the singularity expanded, it's possible that particles were born already entangled, instantly connected in a way that defies our usual understanding of distance and time. Think of it like this: if the Big Bang was the cosmic spark, entanglement could have been the first threads weaving the fabric of reality. These entangled particles, emerging from the chaos of the early universe, might have set the stage for everything that followed. Their connections could explain why the cosmos appears so uniform, as if the universe itself were deeply intertwined from the start. So, was the Big Bang not just the origin of matter and energy, but also the birthplace of quantum entanglement? It's a fascinating idea that ties the very beginning of existence to one of the most mysterious phenomena in physics. And this is just the first of many theories, each one offering a unique perspective on how the universe's first entanglement came to be. Moving forward, let's explore another groundbreaking idea: the inflationary model of the universe. Imagine the cosmos in its earliest moments, expanding faster than the speed of light in a fraction of a second. This rapid growth, known as inflation, didn't just stretch space itself, it could have also created the first entangled particles. Here's how it works. As inflation occurred, tiny quantum fluctuations were stretched across vast distances, freezing into place as the universe cooled. These fluctuations might have given rise to particles that were intrinsically connected, no matter how far apart they ended up. Think of it like a cosmic dance, where every move made by one particle is instantly mirrored by its entangled partner, even across billions of light years. This theory doesn't just explain how entanglement could have emerged, it also sheds light on why the universe looks so uniform on large scales. If entangled particles were woven into the fabric of space during inflation, they could have ensured that distant regions of the cosmos share the same properties as if they were once neighbors. So, was inflation not just a driver of cosmic expansion, but also the mechanism that seeded entanglement throughout the universe? It's a compelling idea that ties together the very large and the very small, showing how the earliest moments of existence might still be shaping the cosmos we see today. Now let's venture into an even more mind-bending idea: the multiverse connection. Picture this: our universe might not be alone. Instead, it could be just one of countless universes, each with its own unique set of physical laws and properties. But here's where things get really fascinating. Quantum entanglement might be the thread that ties these parallel realities together. Imagine entangled particles acting as bridges, connecting different universes in ways we're only beginning to understand. When particles become entangled, their properties are linked no matter how far apart they are. But what if that connection doesn't just span distances within our universe? What if it stretches across realities? This theory suggests that entangled particles could exist in separate universes, yet remain instantaneously connected. It's like having a cosmic phone line between parallel worlds, where changes in one universe could instantly influence another. This idea isn't just science fiction, it's a serious hypothesis that some physicists are exploring to explain the mysteries of quantum mechanics. Could entanglement be the key to understanding the multiverse? And if so, what does that mean for our place in the grand scheme of existence? As we peel back the layers of this theory, we're left with a tantalizing question. Is the universe we see just one piece of a much larger, interconnected puzzle? Now, shifting our focus to a theory that feels like it's straight out of a sci-fi blockbuster, the holographic principle. This idea suggests that our entire universe might be a projection, a kind of cosmic hologram. But what does that actually mean? Imagine the universe as a giant movie screen where everything we see, touch, and experience is like a 2D image projected into a 3D reality. But here's the twist. The information that creates this projection could be stored on a boundary, like the edge of the universe, and guess what connects it all? Quantum entanglement. In this theory, entangled particles are the pixels of this cosmic hologram, carrying the information needed to create the universe as we know it. Just like a hologram appears 3D but is actually encoded on a flat surface, our reality could be encoded on a distant cosmic boundary. This means that every particle, every star, and even you and I might just be entangled information projected into existence. It's a mind-boggling idea that challenges our understanding of space, time, and reality itself. So, how does this tie back to the first quantum entanglement? If the universe is a hologram, then entanglement could be the fundamental process that encodes and connects all the information on this cosmic boundary. It's like the universe's own operating system, where entangled particles are the code that keeps everything running. This theory not only deepens the mystery of entanglement, but also offers a radical new perspective on the nature of existence. Could our reality be nothing more than a vast, interconnected network of entangled information? As we explore this possibility, we're left wondering, what does it mean to be real in a universe that might just be a hologram? Moving forward, let's dive into a theory that takes us to the very fabric of spacetime itself, the quantum foam hypothesis. Picture the universe not as a smooth, continuous expanse, but as a bubbling, seething ocean at the smallest scales imaginable. This is the idea of quantum foam, a frothy, turbulent foundation of spacetime where particles and energy pop in and out of existence in a chaotic dance. At this level, spacetime isn't fixed or stable. Instead, it's constantly fluctuating, creating tiny, fleeting structures that form and dissolve in an instant. Now, here's where things get fascinating. These fluctuations in the quantum foam could be the birthplace of the first quantum entanglement. Imagine these tiny bubbles of spacetime as the cosmic equivalent of a boiling pot of water. Each bubble represents a potential connection, a point where particles could become intertwined. As these bubbles interact, they might create entangled pairs, linking particles across the fabric of spacetime in ways we're only beginning to understand. This theory doesn't just explain how entanglement might have originated, it also reshapes our understanding of reality itself. If spacetime is fundamentally frothy and unstable at its core, then entanglement could be a natural consequence of this chaotic, dynamic environment. It's like the universe is constantly weaving a web of connections with the quantum foam as the loom. But why does this matter? The quantum foam hypothesis offers a glimpse into the very foundation of existence. It suggests that the fabric of reality isn't smooth and predictable, but rather a turbulent sea of potential. By studying these fluctuations, we might uncover the hidden mechanisms that govern everything from the smallest particles to the vastness of the cosmos. It's a theory that challenges us to rethink not just entanglement, but the very nature of spacetime itself. So, what does it mean for our understanding of reality if the universe is built on a bubbling, ever-changing foam? It's a question that keeps physicists and all of us on the edge of our seats. Now, let's turn our attention to one of the universe's most mysterious and powerful phenomena, black holes. These cosmic giants are known for their intense gravitational pull, so strong that not even light can escape. But what if black holes played a role in the very first quantum entanglement? Here's where things take an intriguing twist. When we think of black holes, we often imagine them as devourers of matter and energy. But according to physicist Stephen Hawking, black holes aren't just destructive, they also emit something called Hawking radiation. This radiation is a result of quantum effects near the event horizon, where pairs of particles and antiparticles are constantly being created. While one particle falls into the black hole, the other escapes into space, carrying away energy and gradually causing the black hole to evaporate over time. Here's where entanglement comes into play. The particles in these pairs are intrinsically linked, even if they're separated by vast distances. If one particle falls into the black hole, the other remains entangled with it, creating a connection that defies the boundaries of spacetime. This suggests that black holes, often seen as the end point of matter, could also be the source of entangled particles in the early universe. But why does this matter? If entangled particles emerged from black holes through Hawking radiation, it could provide a mechanism for how entanglement spread across the cosmos. It's like black holes played a dual role, not just as cosmic vacuum cleaners, but also as cosmic weavers, spinning threads of entanglement into the fabric of the universe. This theory challenges our understanding of black holes and their role in the cosmos. It suggests that these enigmatic objects might have been key players in shaping the quantum connections that define reality. So, could black holes be the unsung architects of the universe's first entanglement? It's a question that bridges the gap between quantum mechanics and astrophysics, opening up new avenues for exploration in our quest to understand the universe's deepest secrets. Moving forward, let's explore another fascinating idea: cosmic strings. These hypothetical, one-dimensional defects in spacetime are thought to have formed during the universe's early moments, possibly playing a role in the first quantum entanglement. Imagine spacetime not as a smooth fabric, but as a patchwork quilt with tiny, thread-like flaws. These are cosmic strings. Unlike anything we're familiar with, cosmic strings are incredibly thin yet immensely dense, stretching across vast distances in the cosmos. They're remnants of the early universe, left over from a time when fundamental forces were still unifying. As the universe expanded and cooled, these strings could have formed, creating tension in spacetime itself. Now here's where it gets interesting. These strings aren't just relics of the past, they could have been active players in the universe's quantum story. As cosmic strings vibrate and interact, they might have generated ripples in spacetime, producing pairs of entangled particles. These particles, born from the string's energy, could have become quantumly linked, spreading entanglement across the cosmos. What's particularly intriguing is that cosmic strings are thought to be incredibly stable, meaning they could have persisted long enough to influence the early universe's structure. This raises questions about how these strings might have shaped the distribution of matter and energy, weaving entanglement into the very fabric of reality. Could cosmic strings be the cosmic weavers behind the universe's first entanglement? It's a compelling possibility that ties together the mysteries of quantum mechanics and cosmology. By studying these hypothetical threads, scientists hope to uncover new clues about how the universe's first quantum connections were formed and how they continue to shape the cosmos today. Turning our attention to another intriguing possibility, let's consider the vacuum energy hypothesis. This theory suggests that the very fabric of space, even when seemingly empty, is teeming with energy. These fluctuations, often referred to as quantum vacuum energy, could have been the birthplace of the universe's first entangled particles. Picture the vacuum of space not as a void, but as a bubbling sea of energy, constantly shifting and sparking. These tiny fluctuations, though imperceptible to us, are the result of particles and antiparticles spontaneously appearing and disappearing. It's within this chaotic dance that entanglement might have first emerged. As these fleeting particles interacted, they could have become quantumly linked, creating the first threads of entanglement in the cosmos. What makes this idea even more compelling is its connection to dark energy, the mysterious force driving the accelerated expansion of the universe. Some scientists propose that vacuum energy and dark energy are closely related, if not the same phenomenon. If that's the case, then the same energy responsible for the universe's expansion could also be the source of its first quantum connections. This hypothesis also raises questions about the nature of spacetime itself. Could the vacuum energy fluctuations have left a lasting imprint on the structure of the universe? If so, entanglement might not just be a quantum phenomenon, but a fundamental feature woven into the cosmos itself. By exploring the vacuum energy hypothesis, we gain a deeper understanding of how the universe's most fundamental processes could have shaped its earliest moments. It's a reminder that even the empty spaces of the cosmos are filled with potential, waiting to reveal the secrets of our quantum origins. Now, shifting our focus to another captivating idea, let's explore the quantum gravity connection. This theory suggests that gravity, at its most fundamental level, could have played a pivotal role in creating the universe's first entangled particles. In the early moments of the cosmos, when everything was compressed into an incredibly dense state, the rules of classical physics break down, giving way to quantum mechanics. Here, gravity isn't just a force that pulls objects together. It becomes a quantum phenomenon capable of influencing particles in ways we're only beginning to understand. Imagine gravity at this scale as a delicate web stretching across the fabric of spacetime. As particles interacted under these extreme conditions, the quantum nature of gravity could have caused them to become intricately linked. This entanglement wouldn't just be a fleeting connection, but a fundamental aspect of how particles behaved in the early universe. Some scientists speculate that this quantum gravity link could have been the glue that held the cosmos together during its rapid expansion, ensuring that particles remained connected even as they moved apart. What's particularly fascinating about this theory is how it bridges two of the most significant areas of physics: quantum mechanics and general relativity. These two frameworks, which describe the smallest and largest scales of the universe, have long been at odds with each other. But in the quantum gravity connection, we see a potential harmony where gravity and quantum entanglement work hand in hand to shape the universe. This idea also opens up new questions about the nature of spacetime itself. Could quantum gravity have imprinted a kind of cosmic memory on the universe, where entangled particles carry the echoes of their early interactions? If so, this might explain why entanglement appears to transcend space and time, defying our classical understanding of how the universe operates. By examining the quantum gravity connection, we not only uncover a possible origin for entanglement, but also take a step closer to understanding how the universe's most fundamental forces intertwine. It's a reminder that the cosmos is far more interconnected than we might have ever imagined, with gravity serving as a silent architect of its quantum tapestry. Now, turning our attention to another intriguing possibility, let's delve into the entangled dark matter theory. This idea proposes that dark matter particles, those mysterious and invisible components of the universe, may have been the first to experience quantum entanglement. Dark matter makes up a significant portion of the cosmos, yet we've never directly observed it. Its presence is inferred through its gravitational effects on galaxies and galaxy clusters. But what if entanglement could shed light on its elusive nature? Imagine dark matter particles in the early universe existing in a state of perfect synchronization due to entanglement. These particles, unlike ordinary matter, don't interact with light or electromagnetic forces, making them incredibly difficult to detect. But through entanglement, they could have formed a vast, interconnected network that influenced the structure and evolution of the cosmos. This could explain why dark matter seems to clump together in halos around galaxies, guiding their formation and movement. One of the most compelling aspects of this theory is how it ties into the behavior of dark matter on cosmic scales. If dark matter particles were entangled, their connections would transcend space, allowing them to coordinate their movements and distributions across the universe. This might explain the uniformity we observe in large-scale cosmic structures like the cosmic web, where galaxies are arranged in filaments and voids. Moreover, the entangled dark matter theory could offer insights into why dark matter remains so elusive. If entanglement shields these particles from interacting with ordinary matter and light, it would make them even harder to detect through conventional means. This could also imply that dark matter operates under entirely different physical principles, ones that we're only beginning to grasp. By exploring the idea of entangled dark matter, we're not just unraveling the mystery of its existence, but also gaining a deeper understanding of the universe's hidden architecture. It's a reminder that the cosmos is full of enigmas, and even the most puzzling phenomena might be connected through the threads of quantum entanglement. Now, shifting our focus to the very beginning of everything, let's investigate the primordial singularity entanglement theory. This concept suggests that the universe's initial singularity, the extremely dense and hot state from which the Big Bang emerged, was itself a state of entanglement. Picture this singularity not just as a point of infinite density, but as a tangled web of quantum connections where every particle and force was intrinsically linked. If the singularity was entangled, it would mean that the very fabric of the universe was born interconnected. This entanglement could have set the stage for the universe's evolution, influencing the way matter and energy spread out after the Big Bang. Such a scenario might explain why the cosmos appears so uniform on large scales, as the entangled connections would have ensured a kind of cosmic coherence from the start. Moreover, this theory could provide clues about the nature of spacetime itself. If entanglement was present at the singularity, it might have played a role in shaping the structure of spacetime as we know it. The way spacetime expands, curves, and behaves could have been deeply influenced by these early entangled connections, offering a new perspective on the fundamental forces that govern the universe. The primordial singularity entanglement theory also opens up questions about the nature of the singularity itself. Was it purely a physical phenomenon, or could it have been a state of ultimate quantum entanglement, where all distinctions between particles and forces blurred into one unified whole? Exploring this idea pushes the boundaries of our understanding, challenging us to rethink the origins of existence. By considering the singularity as an entangled state, we're not just looking back at the universe's birth, but also uncovering potential links between quantum mechanics and cosmology. It's a fascinating reminder that even the earliest moments of the cosmos might hold the key to understanding its deepest mysteries. Now, turning our attention to the quantum fluctuation hypothesis, we explore how tiny, random changes in energy during the early universe might have sparked the first entangled particles. Imagine the universe as a vast, churning sea of energy where even the smallest ripples could have profound effects. These quantum fluctuations, though minuscule, could have created pockets of entangled particles, weaving a web of connections that would shape the cosmos. As the universe expanded, these fluctuations grew in scale, acting as seeds for the formation of galaxies and larger cosmic structures. The entangled particles would have influenced the way matter clustered together, guiding the creation of stars, galaxies, and the intricate tapestry of the universe we see today. This theory suggests that the very structure of the cosmos might owe its existence to these early quantum links. What's particularly intriguing is how this hypothesis connects the microscopic world of quantum mechanics with the vastness of the universe. The same fluctuations that led to entanglement on a tiny scale could have determined the distribution of matter on a cosmic scale, bridging the gap between the quantum and the cosmological. It's a powerful reminder of how deeply intertwined the smallest and largest aspects of reality truly are. By understanding the role of quantum fluctuations in entanglement, we gain fresh insights into the origins of the universe's structure. This theory not only explains the uniformity and complexity of the cosmos, but also highlights the enduring influence of the quantum world on the grand stage of the universe. It's a fascinating lens through which to view the earliest moments of existence and their lasting impact. Shifting our focus now to the entangled photon theory, we delve into the idea that photons, the fundamental particles of light, may have been the universe's first entangled particles. Imagine the early cosmos as a glowing sea of light where photons zipped through the dense, hot environment, constantly interacting with each other. In this chaotic setting, it's possible that these particles became entangled, linking their properties in ways that would influence the universe's evolution. This theory suggests that entangled photons could have played a pivotal role in shaping the behavior of light during the universe's infancy. As the cosmos expanded and cooled, these photons would have carried their entangled states across vast distances, potentially leaving imprints on the cosmic microwave background, the faint glow that remains from the Big Bang. This could explain why light appears so uniform and consistent across the universe today. What's particularly fascinating about this idea is how it connects the quantum nature of photons to the large-scale structure of the cosmos. Entangled photons may have acted as a kind of quantum blueprint, guiding the distribution of energy and matter in ways that ultimately led to the formation of stars, galaxies, and the intricate web of the universe. It's a compelling way to see how the smallest particles could have influenced the grandest scales. By exploring the possibility that photons were the first entangled particles, we gain a deeper understanding of how light itself might have shaped the universe's early moments. This theory not only highlights the profound impact of quantum entanglement, but also underscores the enduring legacy of light in the story of the cosmos. It's a vivid reminder that even the most familiar particles, like photons, can hold secrets that redefine our understanding of the universe's origins. Now, let's take a leap into a concept that sounds like it's straight out of science fiction, the quantum wormhole hypothesis. This theory proposes that microscopic wormholes, often imagined as tunnels through space-time, could have been the mechanism behind the universe's first quantum entanglement. Picture these wormholes as tiny bridges linking particles across vast distances, even in the earliest moments of the cosmos. In this scenario, quantum wormholes would have allowed particles to become entangled by creating a direct connection between them, regardless of how far apart they were. These microscopic passages wouldn't just defy our everyday understanding of space and distance, they'd also provide a possible explanation for how entanglement could occur instantly, even between particles separated by the entire universe. What makes this idea so intriguing is its potential to unify the strange behavior of quantum mechanics with the structure of spacetime itself. If quantum wormholes existed in the early universe, they could have acted as invisible threads, weaving entangled particles into the very fabric of reality. This could explain how entanglement, a phenomenon that seems to defy classical physics, became such a fundamental feature of the cosmos. By considering the role of quantum wormholes, we're not just exploring the origins of entanglement, we're also opening the door to a deeper understanding of spacetime's quantum nature. It's a theory that challenges us to rethink the way we see the universe, suggesting that even the smallest structures, like wormholes, could have had a monumental impact on its evolution. Next, we'll turn our attention to another fascinating idea, the entangled neutrino theory, where these elusive particles take center stage in the story of the universe's first quantum entanglement. Now, shifting our gaze to one of the universe's most mysterious inhabitants, let's explore the entangled neutrino theory. Neutrinos, often called the ghost particles of the cosmos, are nearly massless particles that rarely interact with matter. But what if these elusive particles were the first to become entangled in the early universe? This theory suggests that neutrinos, which flooded the universe just seconds after the Big Bang, could have been the pioneers of quantum entanglement. Their unique properties, being able to travel vast distances without interacting with other matter, make them ideal candidates for entanglement. Imagine a universe so dense with neutrinos that they were constantly brushing past each other, creating connections that persisted even as the cosmos expanded. What's fascinating is how neutrinos could have influenced the evolution of the universe. If they were entangled, these particles might have carried information across vast regions of space, seeding the early structures that eventually gave rise to galaxies and cosmic webs. Their entanglement could have acted like an invisible blueprint, guiding the formation of the universe in ways we're only beginning to understand. This theory also challenges us to rethink the role of neutrinos in cosmic history. Often overlooked because of their ghostly nature, neutrinos could have been the silent architects of the universe's quantum framework. By exploring their potential entanglement, we're not just uncovering the origins of quantum connections, we're also shedding light on how even the most elusive particles shape the cosmos. As we move forward, let's dive into another compelling idea: the quantum field interaction hypothesis, where the fundamental forces of nature take center stage in the story of the universe's first entanglement. Now, let's turn our attention to another intriguing possibility: the quantum field interaction hypothesis. This theory proposes that the interactions between quantum fields in the early universe could have been the driving force behind the first entanglement. Quantum fields, which pervade all of space, are the foundation of particles and forces as we know them. But how exactly could these fields have created entangled connections? Picture the early universe as a seething ocean of quantum fields, each one vibrating with energy. As these fields interacted, they could have produced entangled particles, linking them in ways that defy our classical understanding of physics. These interactions wouldn't just be random events, they'd be governed by the fundamental forces of nature: gravity, electromagnetism, and the strong and weak nuclear forces. It's possible that these forces acted like cosmic choreographers, weaving particles together into a delicate dance of entanglement. The implications of this theory are profound. If quantum field interactions were responsible for entanglement, it could mean that the very fabric of reality is woven together by these entangled connections. This would not only explain how particles became linked, but also how the fundamental forces themselves emerged from the chaotic early universe. It's a reminder that the forces we take for granted today, like gravity holding galaxies together or electromagnetism lighting up the stars, might have their roots in these ancient quantum interactions. What's more, this hypothesis challenges us to rethink the nature of the universe itself. If entanglement arose from quantum field interactions, it suggests that the cosmos is far more interconnected than we've ever imagined. Particles separated by vast distances could still be linked, their fates intertwined by the invisible threads of quantum fields. This interconnectedness could have shaped the universe's structure, from the smallest particles to the largest galaxies. As we continue to explore the origins of quantum entanglement, the quantum field interaction hypothesis offers a new perspective on how the universe's first connections might have formed. It's a theory that not only deepens our understanding of entanglement, but also highlights the intricate role of the fundamental forces in shaping the cosmos. And with that, let's venture into the next chapter of our journey, where we'll examine how quarks, the building blocks of matter, might have played a role in the universe's first entanglement. Now, let's dig deeper into the fascinating idea that quarks, the tiniest building blocks of matter, might have been the first entangled particles in the universe. Quarks are fundamental particles that combine to form protons and neutrons, which in turn make up the atomic nuclei of everything around us. But what if their entanglement played a pivotal role in the formation of matter itself? Imagine the early universe, a hot, dense soup of quarks and other particles. In such extreme conditions, quarks wouldn't exist in isolation. Instead, they'd be constantly interacting, colliding, and binding together. It's possible that these interactions led to entanglement, linking quarks in pairs or groups. This entanglement wouldn't just be a random phenomenon. It could have been a crucial factor in how quarks combine to form protons and neutrons. Think of it like this: entanglement could have acted as a kind of cosmic glue, holding quarks together in stable configurations. Without this quantum connection, quarks might not have been able to form the particles that eventually gave rise to atoms, stars, and galaxies. It's a theory that suggests entanglement wasn't just a byproduct of the early universe. It was a driving force behind the very structure of matter. This idea also has implications for our understanding of the strong nuclear force, which binds quarks together inside protons and neutrons. Could entanglement have played a role in how this force operates? Some researchers believe that entanglement might be deeply intertwined with the strong force, influencing how quarks interact and stay bound together. If true, this would mean that entanglement is not just a mysterious quantum phenomenon, but a fundamental aspect of the forces that govern the universe. The entangled quark theory also raises questions about the nature of matter itself. If quarks were entangled, it could mean that every proton and neutron in the universe carries a hidden quantum connection, a legacy of the universe's earliest moments. This could explain why matter behaves the way it does and why certain particles are so stable despite the chaos of the early cosmos. As we explore this theory, it's clear that the entanglement of quarks could have been a cornerstone in the formation of the universe. It's a reminder that even the smallest particles might hold the key to understanding the biggest mysteries. And with that, let's shift our focus to the next intriguing possibility, where we'll examine how quantum coherence in the early universe could have stabilized the cosmos. Now, let's turn our attention to another intriguing possibility: the idea that quantum coherence in the early universe might have been the key to both entanglement and the stability of the cosmos itself. Quantum coherence refers to the phenomenon where particles behave as a unified system, maintaining a consistent quantum state. In the chaotic environment of the early universe, this coherence could have played a critical role in preventing the cosmos from descending into complete disorder. Picture the universe just moments after its birth, a seething, unstable sea of energy and particles. Without some form of organizing principle, this chaos could have led to a universe that quickly fell apart. Quantum coherence might have been that principle, acting like a cosmic conductor that kept particles in sync. This synchronization wouldn't just have prevented chaos, it could have enabled particles to become entangled on a massive scale. Entanglement in this context would have been a natural consequence of coherence. As particles interacted and aligned their quantum states, they would have formed connections that transcended space and time. These entangled connections could have provided a framework for the universe to evolve in an orderly way, allowing structures like galaxies and stars to form. Without coherence, the early universe might have remained a turbulent, formless expanse. The role of quantum coherence doesn't stop there. It could also explain why the universe appears so finely tuned. Coherence would have ensured that particles interacted in predictable ways, setting the stage for the laws of physics as we know them. This might also shed light on why certain constants, like the speed of light or the strength of gravity, have the precise values they do. In a coherent universe, these constants wouldn't be random. They'd be the result of quantum interactions that were locked into place early on. This theory also raises fascinating questions about the nature of reality. If coherence was so essential in the early universe, does it still play a role today? Some scientists believe that coherence could be at the heart of phenomena like superconductivity or even photosynthesis. suggesting that it might be a fundamental aspect of nature. As we explore this idea, it's clear that quantum coherence could have been one of the universe's most important organizing principles. It's a reminder that even in chaos there can be harmony, a harmony that might have been woven into the fabric of the cosmos from the very beginning. And with that, let's move on to the next theory, where we'll investigate the possibility that cosmic rays were entangled in the early universe, shaping its evolution in unexpected ways. Shifting our focus to the skies, let's delve into the fascinating theory that cosmic rays might have been among the first entangled particles in the universe. Cosmic rays are highly energetic particles that travel through space at nearly the speed of light, originating from sources like supernova, black holes, and even the Big Bang itself. But what if these particles weren't just random travelers? What if they were interconnected through quantum entanglement, playing a pivotal role in the universe's evolution? The origins of cosmic rays trace back to some of the most violent and energetic events in the cosmos. When a star explodes in a supernova, it sends shockwaves rippling through space, accelerating particles to immense speeds. Similarly, the intense gravitational fields around black holes can hurl particles across vast distances. In the early universe, these processes could have been even more extreme, creating an environment ripe for entanglement. Imagine these high-energy particles colliding and interacting in the chaotic aftermath of the Big Bang. Under such conditions, it's possible that some of these particles became entangled, forming connections that transcended space and time. These entangled cosmic rays could have carried information and energy across the universe, influencing the formation of cosmic structures. One intriguing possibility is that entangled cosmic rays helped shape the large-scale structure of the universe. As these particles interacted with matter, they might have influenced the distribution of galaxies and galaxy clusters. This could explain why the universe appears so uniform on a large scale, with structures arranged in a kind of cosmic web. The entanglement of these particles could have acted as a guiding force, ensuring that the universe evolved in an orderly and interconnected way, but the implications don't stop there. Entangled cosmic rays could also provide clues about the nature of dark matter. Some scientists speculate that dark matter particles might have been entangled with cosmic rays, creating a hidden web of connections that we're only beginning to understand. This could shed light on why dark matter remains so elusive. It might be intricately linked to the entangled particles that zipped through the early universe. As we explore this theory, it's clear that cosmic rays could have been more than just high-energy travelers. They might have been part of a vast, entangled network that shaped the universe in its earliest moments. This idea invites us to rethink our understanding of cosmic rays, seeing them not just as remnants of cosmic events, but as active participants in the universe's story. And with that in mind, let's move on to the next theory, where we'll examine how particle collisions in the early universe might have created the first entanglement. Now, turning our attention to the explosive dynamics of the early universe, let's explore the quantum collision hypothesis. In the chaotic moments following the Big Bang, the universe was a seething cauldron of particles zipping around at incredible speeds, colliding with one another in a frenzy of energy and activity. It's within these high-energy collisions that scientists believe the first instances of quantum entanglement may have emerged. Picture this: particles smashing into each other with such force that their identities and properties become intertwined. In the extreme conditions of the early universe, these collisions weren't just brief encounters, they were transformative events. As particles collided, their quantum states could have become entangled, creating a deep connection that persisted even as they moved apart. This entanglement could have been a fundamental process, weaving a complex web of relationships between particles that would shape the fabric of the cosmos. But why does this matter? These entangled particles didn't just exist in isolation. They played a crucial role in the formation of matter as we know it. For instance, quarks, the building blocks of protons and neutrons, could have become entangled during these collisions, influencing how they combined to form the first atomic nuclei. Without these entangled interactions, the universe might have remained a featureless soup of particles, never coalescing into the intricate structures we see today. Moreover, the quantum collision hypothesis has profound implications for our understanding of the early universe's symmetry and balance. Entanglement could have provided a mechanism for particles to share information instantaneously, ensuring that the universe evolved in a coherent and organized way. This might explain why certain fundamental forces like electromagnetism and the strong nuclear force exhibit such precise behaviors. Entanglement could have acted as a kind of cosmic glue, holding the universe together in its formative stages. As we piece together this theory, it's clear that particle collisions weren't just random events. They were the sparks that ignited entanglement, setting the stage for the universe's evolution. And with that in mind, let's move forward to uncover how entanglement might have been facilitated by another fascinating phenomenon in the early universe. Now, shifting our focus to a state of matter that defies everyday intuition, let's delve into the entangled Bose-Einstein condensate theory. In the extreme conditions of the early universe, the intense heat and density created an environment where particles behaved in ways that seem almost otherworldly. Among these exotic states was the Bose-Einstein condensate, a phenomenon where particles lose their individual identities and merge into a single, unified quantum state. Imagine the universe at this stage as a vast, interconnected web, where particles no longer act independently but instead move in perfect harmony. In this state, countless particles could have shared the same quantum properties, creating a system where entanglement wasn't just possible, it was inevitable. The Bose-Einstein condensate would have acted as a cosmic stage, enabling particles to become entangled on an unprecedented scale. What sets this theory apart is the unique nature of the Bose-Einstein condensate itself. Unlike ordinary matter, a condensate exists at temperatures close to absolute zero, where particles slow down dramatically and their quantum behaviors become dominant. In the early universe, this state could have been achieved naturally, allowing particles to form entangled bonds that persisted as the cosmos expanded and cooled. The implications of this theory are profound. If entanglement originated within a Bose-Einstein condensate, it would suggest that the universe's earliest moments were governed by a kind of quantum unity where particles were deeply interconnected. This could explain why we observe such coherent behaviors in the cosmos today, from the uniformity of the cosmic microwave background to the structured formation of galaxies. Moreover, this theory provides a window into the role of quantum mechanics in shaping the universe's evolution. The entanglement facilitated by a Bose-Einstein condensate might have acted as a precursor to the complex interactions we see in modern physics, laying the groundwork for the laws that govern our reality. As we explore this idea, it's clear that the early universe was not just a chaotic soup of particles but a finely tuned quantum system, where phenomena like Bose-Einstein condensates played a pivotal role in weaving the fabric of reality. And with this in mind, let's turn our attention to another intriguing theory that examines the role of quantum decoherence in the universe's first entanglement. Now, let's venture into the fascinating realm of the quantum decoherence hypothesis. This theory offers a unique perspective on how the universe's first entanglement might have been influenced by the process of quantum decoherence. To understand this, we first need to grasp what decoherence is. In simple terms, quantum decoherence refers to the loss of quantum coherence, the phenomenon where quantum systems lose their ability to exhibit interference effects due to interactions with their surroundings. In the early universe, particles existed in a state of quantum superposition, meaning they could simultaneously occupy multiple states or positions. However, as the universe expanded and cooled, these particles began to interact with their environment, leading to decoherence. This process effectively collapsed their quantum states into definite outcomes, marking the transition from the quantum realm to the classical world we observe today. But here's where it gets intriguing. Some scientists propose that before decoherence fully took hold, entanglement might have been a dominant feature of the early universe. As particles interacted and decohered, they could have left behind entangled pairs or systems that retained their quantum connections despite the transition. This suggests that the first quantum entanglement might have been a product of decoherence itself, a kind of quantum imprint that persisted even as the universe evolved into its classical state. The implications of this hypothesis are profound. It bridges the gap between quantum mechanics and classical physics, offering a potential explanation for how the strange behaviors of the quantum world gave rise to the familiar laws of our macroscopic reality. If entanglement played a role in this transition, it could mean that the universe's earliest moments were not just a collection of random events but a carefully orchestrated process where decoherence and entanglement worked hand in hand to shape the cosmos. Moreover, this theory highlights the dynamic interplay between quantum systems and their environments. It suggests that entanglement might have been a byproduct of the universe's attempts to stabilize itself as it transitioned from a quantum state to a classical one. This perspective not only deepens our understanding of the early universe, but also underscores the intricate balance between chaos and order that defines the fabric of reality. As we reflect on this idea, it's clear that quantum decoherence wasn't just a process of loss, it was a mechanism that might have preserved certain quantum connections, influencing the universe's structure and behavior in ways we're only beginning to comprehend. With this in mind, let's turn our attention to another compelling theory that explores the role of entangled dark energy in the cosmos. Moving forward, let's explore the intriguing possibility that dark energy itself might have been entangled in the early universe. Dark energy, the mysterious force driving the accelerated expansion of the cosmos, remains one of the greatest puzzles in modern physics. But what if its behavior is tied to quantum entanglement? This theory suggests that dark energy particles could have been entangled during the universe's earliest moments, influencing the way the cosmos expanded over time. Here's how it might work. In the early universe, particles and energy existed in an incredibly dense and hot state, where interactions were intense and frequent. If dark energy particles were entangled, their quantum connections could have created a network of influence across vast distances. As the universe expanded, these entangled particles might have continued to interact, subtly guiding the rate of cosmic expansion. This idea could help explain why the universe's expansion is accelerating. If entangled dark energy particles were spread throughout space, their quantum links could have created a kind of push that counteracts gravity on large scales. This would align with observations of distant galaxies moving away from us faster than expected. Moreover, this theory offers a potential bridge between quantum mechanics and cosmology. It suggests that the quantum properties of dark energy particles might have played a crucial role in shaping the universe's large-scale structure. If entanglement influenced dark energy, it could mean that the accelerated expansion we see today is a direct result of quantum interactions from the early universe. This perspective also opens up new questions about the nature of dark energy itself. Could it be that dark energy isn't just a uniform force but a collection of entangled particles working in concert? And if so, what implications does this have for our understanding of the cosmos? As we ponder this theory, it's clear that entanglement might hold the key to unraveling some of the universe's deepest mysteries. From the smallest particles to the vastness of space, quantum connections could be shaping the cosmos in ways we're only beginning to comprehend. Next, we'll delve into how quantum information processing might have played a role in the universe's first entanglement. Shifting our focus, let's explore the idea that the universe's first entanglement might have been driven by quantum information processing. Information is often thought of as something intangible, but in the quantum world, it's a fundamental building block of reality. The quantum information hypothesis suggests that entanglement could have arisen as a result of how information was processed and shared in the early universe. At its core, quantum mechanics is deeply tied to information. Every particle, every interaction, and every quantum state can be described in terms of information. In the early universe, this information wasn't static. It was dynamic, constantly being exchanged and transformed. If particles were sharing and processing information, it's possible that entanglement emerged as a natural consequence of this activity. Think of it like a cosmic conversation where particles talk to each other through their quantum states, creating connections that transcend space and time. This theory also offers a fascinating perspective on the emergence of complexity in the universe. As entangled particles interacted and processed information, they could have formed networks of influence that shaped the development of larger structures. Over time, these networks might have grown more intricate, leading to the formation of galaxies, stars, and even life itself. In this view, entanglement isn't just a property of particles, it's a mechanism that drove the universe from simplicity to complexity. What's particularly intriguing is how this ties into the concept of a quantum computer operating on a cosmic scale. If the early universe was processing information through entanglement, it could have been laying the groundwork for the intricate and interconnected cosmos we see today. This idea blurs the line between physics and computation, suggesting that the universe itself might function as a vast quantum computational system. The quantum information hypothesis also raises profound questions about the nature of reality. If entanglement is linked to information processing, does that mean the universe is fundamentally shaped by information? And if so, what does this imply about the origins of complexity and the forces that govern existence? These are questions that challenge our understanding of everything from the smallest particles to the largest cosmic structures. As we consider this theory, it's clear that entanglement and information are deeply intertwined. The quantum information hypothesis offers a fresh lens through which to view the universe's earliest moments, suggesting that the seeds of complexity were sown through the intricate dance of quantum information and entanglement. Next, we'll turn our attention to another fascinating idea: how the universe's plasma state might have facilitated entanglement in its formative stages. Building on the idea of quantum information processing, let's now examine how the universe's plasma state might have been a crucial stage for the first quantum entanglement. In the early cosmos, matter existed not as atoms or molecules, but as a seething, energetic plasma, a state where particles are so hot and energetic that electrons are stripped away from their nuclei. This plasma was a chaotic soup of charged particles, constantly colliding and interacting, and it's within this environment that entanglement could have flourished. In such a high-energy state, particles were in constant motion, exchanging energy and information at an incredible rate. This intense activity created the perfect conditions for entanglement to emerge. Imagine the plasma as a vast, interconnected network where particles were constantly talking to one another, their quantum states linked in ways that defied classical physics. These entangled connections could have acted as the glue that held the early universe together, influencing how matter clumped and evolved over time. The significance of this theory becomes even clearer when we consider the formation of stars and galaxies. As the universe cooled and expanded, the plasma began to condense into denser regions, eventually giving rise to the first stars and galaxies. If entanglement was already present in the plasma, it could have played a key role in shaping these structures. Entangled particles might have influenced how matter clustered, creating the scaffolding for the cosmic web we observe today. In this way, entanglement wasn't just a side effect of the plasma state, it could have been a driving force behind the universe's large-scale structure. Moreover, the entangled plasma theory offers a unique perspective on the transition from chaos to order in the early cosmos. While the plasma was a turbulent and disordered environment, entanglement could have introduced a subtle kind of coherence, guiding the universe toward the formation of more complex and organized systems. This idea bridges the gap between the quantum realm and the macroscopic world, suggesting that the seeds of cosmic structure were planted at the smallest scales. As we reflect on this theory, it's fascinating to consider how entanglement might have shaped the universe's evolution. From the fiery plasma of the early cosmos to the intricate galaxies that fill the sky today, the connections forged in those first moments could have left an indelible mark on the fabric of reality. Next, we'll explore how quantum tunneling might have played a role in creating entangled particles, adding another layer to our understanding of the universe's quantum origins. Turning our attention to another fascinating possibility, let's explore how quantum tunneling might have been a key player in the universe's first entanglement. Quantum tunneling is one of those mind-bending phenomena where particles overcome energy barriers that, according to classical physics, should be impossible to surmount. Think of it like a ball rolling up a hill and magically appearing on the other side without ever climbing over it. In the early universe, this process could have been crucial in creating entangled particles. Picture the universe in its earliest moments, filled with immense energy and constant fluctuations. Under such extreme conditions, particles had to navigate a landscape of towering energy barriers. Quantum tunneling allowed them to tunnel through these barriers effortlessly, enabling interactions that would have otherwise been impossible. This tunneling could have brought particles into close enough proximity to become entangled, linking their quantum states in ways that persisted even as the universe expanded. The implications of this hypothesis are profound. Quantum tunneling not only facilitated entanglement, but also played a role in shaping the early universe's evolution. By allowing particles to overcome energy barriers, it enabled processes like nucleosynthesis, the formation of the first atomic nuclei, and the eventual emergence of matter as we know it. Entanglement, born from tunneling, could have acted as a subtle yet powerful force, guiding the universe's development from its chaotic infancy to its structured maturity. What's particularly intriguing is how quantum tunneling bridges the gap between the quantum and cosmic scales. While it operates at the tiniest levels, its effects ripple outward, influencing the formation of galaxies and the large-scale structure of the cosmos. This hypothesis reminds us that even the most mysterious quantum phenomena might hold the keys to understanding the universe's grand design. As we wrap up this theory, it's worth considering how quantum tunneling and entanglement together might have set the stage for the complex universe we inhabit today. Next, we'll delve into the intriguing idea that superstrings, tiny, vibrating filaments, could have been the source of the universe's first entanglement, adding yet another layer to this cosmic mystery. Now, let's shift gears and explore the captivating idea of superstrings and their potential role in the universe's first entanglement. Superstring theory suggests that the fundamental building blocks of reality are not point-like particles but tiny, vibrating filaments called strings. These strings, oscillating at different frequencies, are thought to give rise to all the particles and forces we observe in the cosmos. But here's where it gets even more fascinating. These strings might have also been the catalysts for the first quantum entanglement. Imagine the early universe as a cosmic symphony, with superstrings vibrating and interacting in perfect harmony. As these strings moved and collided, their vibrations could have created intricate connections between particles, entangling their quantum states. This entanglement wouldn't just be a random occurrence, but a natural consequence of the strings' interactions, weaving a delicate web of interconnectedness that stretched across the cosmos. What makes this theory so compelling is how it ties together quantum mechanics and the fabric of space-time. Superstring theory proposes that these strings aren't just floating in space, they are the very fabric of space itself. This means that entanglement, emerging from the strings' vibrations, could have been woven into the structure of the universe from the very beginning. It's a concept that blurs the line between particles and space-time, suggesting that entanglement might be a fundamental feature of reality itself. The implications are staggering. If superstrings were the source of the first entanglement, it could mean that the interconnectedness we observe in quantum systems is a remnant of the universe's earliest moments. This hypothesis also opens up new avenues for understanding phenomena like black holes and the nature of dark matter, as the behavior of superstrings could hold clues to these cosmic mysteries. As we reflect on this theory, it's clear that superstrings offer a unique perspective on how entanglement might have originated. Next, we'll dive into the intriguing concept of quantum spin and how it could have played a pivotal role in the universe's first entanglement, adding yet another layer of complexity to this cosmic puzzle. Turning our attention to another fascinating concept, let's explore how quantum spin might have played a crucial role in the universe's first entanglement. Quantum spin is an intrinsic property of particles, much like their charge or mass, but it's not about physical spinning in the traditional sense. Instead, it's a fundamental characteristic that influences how particles interact with each other and with magnetic fields. In the early universe, as particles were forming and interacting, their quantum spins could have created the conditions for entanglement. Imagine two particles with spins that are inherently linked. When one particle's spin changes, the other instantly adjusts, no matter how far apart they are. This phenomenon, known as spin entanglement, could have been one of the earliest forms of quantum connection, binding particles together in a web of interdependent states. What makes this hypothesis particularly intriguing is its connection to the behavior of subatomic particles. Spin entanglement isn't just a theoretical curiosity. It's been observed in experiments showing that particles can remain deeply connected even across vast distances. This suggests that spin interactions could have been a driving force in establishing the entangled relationships that we see in quantum systems today. The implications of this theory are profound. If spin interactions were the source of the first entanglement, it could mean that this fundamental property of particles was instrumental in shaping the early universe. It also provides a new way to understand phenomena like quantum tunneling and the behavior of particles in extreme environments, such as those near black holes. As we consider the role of quantum spin in entanglement, it's clear that this property is more than just a feature of particles. It's a potential key to unlocking the mysteries of the cosmos. Next, we'll delve into the intriguing possibility that the Higgs field, known for giving particles mass, might also have been a facilitator of the universe's first entanglement, adding yet another layer to this cosmic puzzle. Shifting our gaze to another cornerstone of modern physics, let's consider the idea that the Higgs field, best known for giving particles their mass, might also have played a pivotal role in the universe's first quantum entanglement. The Higgs field permeates all of space, interacting with particles in a way that endows them with mass. But what if this field did more than just determine how heavy or light particles are? What if it also served as a cosmic bridge connecting particles through entanglement? In the early moments of the universe, as the Higgs field began to take shape, it could have created the conditions for entanglement to emerge. Imagine particles interacting with this field, not just to gain mass, but also to become intertwined in a web of quantum connections. This would mean that the very mechanism responsible for mass could have also been responsible for establishing the first entangled relationships between particles. It's a fascinating possibility that adds a new dimension to our understanding of the Higgs field. This theory gains even more intrigue when we consider how the Higgs field interacts with different types of particles. For example, some particles interact strongly with the Higgs field, while others barely interact at all. This variation in interaction could explain why certain particles are more likely to become entangled than others. It also offers a potential link between entanglement and the hierarchy of particle masses, suggesting that the two phenomena might be deeply connected. If the Higgs field did indeed facilitate entanglement, it could have had profound implications for the structure of the early universe. Entangled particles bound together through the Higgs field could have influenced the formation of matter and the development of cosmic structures. This would mean that the Higgs field didn't just shape the universe by giving particles mass, it also shaped it by weaving a quantum tapestry of interconnected particles. As we ponder the role of the Higgs field in entanglement, it's clear that this field is far more than just a mass-giving mechanism. It could be a fundamental force that ties the universe together, both in terms of mass and quantum connections. Next, we'll explore the captivating and speculative idea that consciousness itself might have played a role in the universe's first entanglement, opening the door to even more profound questions about the nature of reality. Now, let's venture into one of the most intriguing and speculative theories, the idea that consciousness itself might have played a role in the universe's first quantum entanglement. This hypothesis stretches the boundaries of science and philosophy, suggesting that the act of observation or awareness could have influenced the quantum world in its earliest moments. At its core, this theory ties into the observer effect, a phenomenon in quantum mechanics where the act of measuring or observing a particle can alter its state. Imagine the universe in its infancy, a chaotic sea of particles and energy. Now consider the possibility that consciousness in some form existed even then. Could this consciousness have acted as a kind of quantum observer, causing particles to become entangled through the act of seeing or interacting with them? It's a bold idea that challenges our understanding of both physics and the nature of awareness. This theory doesn't just raise questions about the origin of entanglement, it opens up profound philosophical debates. If consciousness played a role in the universe's first entanglement, does that mean the mind has a fundamental place in the fabric of reality? Could it suggest that the universe itself has a form of awareness, or that consciousness is a fundamental force, much like gravity or electromagnetism? These questions blur the lines between science and metaphysics, offering a fresh perspective on the age-old problem of the relationship between mind and matter. The connection to the observer effect adds another layer of intrigue. In quantum experiments, particles seem to choose their state only when observed, leading to the idea that reality itself is shaped by observation. If this principle extends back to the universe's first moments, it could mean that entanglement wasn't just a random occurrence but a process influenced by the presence of an observer, whether that's a conscious entity or something more abstract. While this theory remains highly speculative and controversial, it serves as a reminder of how much we still don't understand about the universe. It challenges us to think beyond traditional physics and consider the possibility that consciousness isn't just a byproduct of the universe but an integral part of its very foundation. As we reflect on this idea, it's clear that the mystery of the universe's first entanglement continues to inspire both scientific inquiry and philosophical wonder. Each theory we've explored offers a unique lens through which to view this profound cosmic event, reminding us of the endless complexity and beauty of the universe we inhabit. Next, we'll wrap up our journey by revisiting the 30 theories we've discussed and reflecting on what they reveal about the origins of quantum entanglement. As we bring this exploration to a close, it's remarkable to reflect on the sheer diversity of ideas we've uncovered about the universe's first quantum entanglement. From the Big Bang to cosmic strings, and from quantum foam to the enigmatic role of consciousness, each theory offers a unique window into this profound cosmic mystery. These 30 perspectives remind us just how intricate and multifaceted our universe truly is, filled with endless questions waiting to be answered. What stands out is how these theories span the spectrum of science and philosophy, blending hard physics with speculative thought. They challenge our assumptions, push the boundaries of our understanding, and invite us to imagine possibilities that once seemed beyond reach. Whether it's the idea of entangled particles emerging from the primordial singularity, or the notion that dark matter itself was the first to become entangled, each concept adds a layer of depth to our quest to unravel the universe's secrets. Yet, for all the progress we've made, the mystery of quantum entanglement remains unsolved. It's a reminder that science is an ever-evolving journey, one that thrives on curiosity, creativity, and collaboration. The beauty of this topic lies not just in the answers we've found, but in the questions it continues to inspire. What truly sparked the first entanglement? How does it shape the cosmos we see today? These are the kinds of questions that fuel our exploration of the unknown. So, as we wrap up, I'd love to hear your thoughts. Which of these theories resonated with you the most? Do you have your own ideas about the origins of quantum entanglement? Share your thoughts in the comments below. This is a conversation that thrives on diverse perspectives. If you enjoyed this deep dive into the mysteries of the universe, don't forget to subscribe and hit the notification bell for more content like this. The cosmos is full of wonders waiting to be explored, and I can't wait to take you on the next journey. Until then, keep wondering, keep questioning, and keep exploring the endless mysteries of our incredible universe.